Hello. Welcome to Earth Science. In this video recording, we will continue our last lesson in Module 1. The formation of the unique Earth. Our Earth is one of the 8 planets among the solar system. It belongs to the inner planets or the planets closest to the Sun. These are Mercury, Venus, Earth, Mars. Inner planets are also called terrestrial planets, because of its characteristic. Geologically, the inner planets are all made of cooled igneous rock with iron cores, and all have been geologically active, at least early in their history. None of the inner planets has rings. Meanwhile, the outer planets Jupiter, Saturn, Uranus, and Neptune are sometimes called Jovian planets or gas giants because they are huge planets of gas. They also have rings, and each of the gas planets has plenty of moons. Now, what is all about the solar system? 4.6 billion years ago, our solar system have formed. Our solar system is a part of a spiral galaxy known as the Milky Way. The Sun, the center of our solar system, holds 8 planets and countless smaller objects in its orbit. Question. Name the type of galaxy in which our solar system belongs to. You may recall Edwin Hubble's classification of galaxies in this. Answer. Spiral galaxy. Our solar system is a part of a spiral galaxy known as the Milky Way. The Sun, the center of our solar system, holds 8 planets and countless smaller objects in its orbit, including 100 billion stars and other bodies. Question. He is one of the famous philosophers in history to establish the first widely accepted ideas about the structure of the universe. Answer. Aristotle. With his Aristotelian universe. Aristotle was a Greek philosopher and polymath during the classical period in ancient Greece. Taught by Plato, he was the founder of the Lyceum, a school of philosophy, and the Aristotelian tradition. Scientists had formulated ideas on how the motion of the planets occurred, and how all the heavenly orbs fit together. This gave rise to the geocentric model of the universe. Ancient philosophers and astronomers accepted as first principles that Earth was located at the center and that everything in the heavens moved in uniform circular motion. Question. He developed a revolutionary astronomical model that positioned the Sun near the center of the universe, motionless, with Earth and other planets orbiting around it in circular paths, modified by epicycles. Answer. Nicolaus Copernicus. Nicolaus Copernicus was a Renaissance-era mathematician and astronomer, who formulated a model of the universe that placed the Sun rather than Earth at the center of the universe. The Copernican model. This model is called a heliocentric system. The ordering of the planets known to Copernicus in this new system is illustrated in the following figure, which we recognize as the modern ordering of those planets. To explain the daily annual cycles of the sky, he proposed that Earth rotates on its axis and revolves around the Sun. Question. What makes the solar system into forming a disk-like shape? Answer. The continuous spinning from a collapsed solar nebula. The orbits of the planet lie on the same plane because of the rotating solar nebula collapsed into a disk, and the planets formed in the disk. What are the large-scale features of the solar system? Concentration is at the center while angular momentum is held by the outer planets. Orbits of the planets are elliptical and are on the same plane. All planets revolve around the Sun. The periods of revolution of the planets increase with increasing distance from the Sun. The innermost planet moves fastest, the outermost, the slowest. All planets are located at regular intervals from the Sun. Question. Which among the planets are the results of catastrophic events such as off-center collisions with a massive planetesimal or a massive small planets? Answer. Venus and Uranus. Catastrophic events like off-center collisions with a massive planetesimal might have caused the odd rotations of Venus and Uranus. This is what we call retrograde motion, or the reverse rotation following a clockwise direction of east to west. When standing on Earth and observing the night sky, all of the planets move on a west to east track through the stars. Question. It is a region in the solar system, located roughly between the orbits of the planets Jupiter and Mars, that is occupied by a great many solid, irregularly shaped bodies, of many sizes but much smaller than planets, called asteroids or minor planets. Answer. Asteroid belt. The asteroids seen today are the last remains of those rocky planetesimals. These rocky planetesimals could have formed a planet just inward from Jupiter's orbit, instead collided at high speeds and shattered rather than combining. Now let's discuss the different hypotheses on the birth and formation of the solar system. Question. This term is referred to the interstellar clouds that contract on its gravity and begin to rotate. Answer. Nebulae. A nebula is an interstellar cloud of dust, hydrogen, helium and other ionized gases. Originally, the term was used to describe any diffused astronomical object, including galaxies beyond the Milky Way. Some nebulae come from a dying star, such as a supernova. A supernova is the explosion of a star. It is the largest explosion that takes place in space. In 1700s, Emmanuel Swedenborg, Immanuel Kant, and Pierre-Simon Laplace. The nebular hypothesis is the most widely accepted model in the field of cosmogony to explain the formation and evolution of the solar system, as well as other planetary systems. It suggests that the solar system formed from gas and dust orbiting the sun. According to this theory, the Sun and all the planets of our solar system began as a giant cloud of molecular gas and dust. Then, about 4.57 billion years ago, something happened that caused the cloud to collapse. This could have been the result of a passing star, or shock waves from a supernova, but the end result was a gravitational collapse. From this collapse, pockets of dust and gas began to collect into denser regions. As the denser regions pulled in more and more matter, conservation of momentum caused it to begin rotating, while increasing pressure caused it to heat up. Most of the material ended up in a ball at the center while the rest of the matter flattened out into disk that circled around it. Collapsing clouds of gas and dust in nebular hypothesis. Here is how a solar system forms in summary. Basically, stars form in gravitationally contracting clouds. This is the first stage of creating the protostars, or the early age of formation of stars from a gravitational collapse. The spinning nebula flattens. Because of the competing forces associated with gravity, gas pressure, and rotation, the contracting nebula begins to flatten into a spinning flattened shape with a bulge at the center. The reduced angular momentum support near the poles means that it is easier for material to fall in near the top, rather than at the equator. Therefore, a bulge eventually leads to disk. Condensation will become the Sun and the planets, as well as their moons and other debris in the solar system. The spinning nebula flattens. Because of the competing forces associated with gravity, gas pressure, and rotation, the contracting nebula begins to flatten into a spinning flattened shape with a bulge at the center. Emissions of ultraviolet radiation soon occurred due to the increased core temperature. As it grows, more materials get into the core, leads to ignition and light production. The nebular hypothesis may enter into stages after forming a protostars. Protostars turn into a brown dwarf or a failed star, if temperature of 10 million Kelvin is not reached. When the protostar does not obtain enough mass of hydrogen to sustain the nuclear fusion. Brown dwarfs are what you get when this process fails. Nucleosynthesis or thermonuclear reaction occurs when temperature reaches 10 million Kelvin. Nucleosynthesis is the process that creates new atomic nuclei from pre-existing nucleons, protons and neutrons, and nuclei. Planetesimal theory was proposed by Forrest R. Moulton and Thomas C. Chamberlain about 1900. It states that the planets were formed by the accumulation of extremely small bits of matter that revolved around the Sun. This matter was produced when a passing star almost collided with the Sun. According to the planetesimal hypothesis, when a planetary system is forming, there is a protoplanetary disk with materials from the nebulae from which the system came. This is the stage of condensation. Accretion. This material is gradually pulled together by gravity to form small chunks. These chunks get larger and larger until they form planetesimals, beginning of growth of protoplanets. Many of the objects break apart when they collide, but some continue to grow. One of the earliest theories for the formation of the planets was called the encounter hypothesis. These theories propose that the planets formed from material ejected from the Sun or a companion star during an encounter with another object. First theory by James Jean in 1917 have invoked an approach or collision involving another star, protostar, or a giant molecular cloud would condense to the formation of planets. The last theory, by George de Buffon in 1949, postulated that a comet collided with the Sun that sent matter into formation of planets. In this scenario, a rogue star or a star that has escaped its home galaxy and is moving independently in or towards the intergalactic void, passes close to the Sun about 5 billion years ago. Material, in the form of hot gas, is tidally stripped from the Sun in the rogue star. This material fragments into smaller lumps which form the planets. This hypothesis has the advantage of explaining why the planets all revolve in the same direction, from the encounter geometry, and also provides an explanation for why the inner worlds are denser than the outer worlds. When it comes to how the Earth was formed, forces that can only be described as fiery, chaotic, and indeed godlike, were involved. The planetesimal theory is a theory on how planets form. According to the planetesimal hypothesis, when a planetary system is forming, there is a protoplanetary disk with materials from the nebulae from which the system came. This material is gradually pulled together by gravity to form small chunks. These chunks get larger and larger until they form planetesimals. Question: what is the main reason for the primitive Earth to be an ocean of molten magma? Answer: rampant volcanic eruption. Much of the Earth was molten because of frequent collisions with other bodies which led to extreme volcanism. It is believed that collisions have been severe, that it generates too much heat, that melted the rock materials forming the early Earth. Planetary differentiation is the process of separating out different constituents of a planetary body as a consequence of their physical or chemical behavior, where the body develops into compositionally distinct layers. The denser materials of a planet sink to the center, while less dense materials rise to the surface, generally in a magma ocean. Such a process tends to create a core and mantle. Sometimes a chemically distinct crust forms on top of the mantle. Question: identify whether true or false. A magnetic compass does not point to the geographic North Pole. Answer: true. In the illustration, the magnetic poles are represented as red line and geographic line is represented as green line and is separated by 10 degrees. The Earth spins around the geographic poles, but magnetic compasses point to the magnetic poles. The magnetic compass points to the Earth's magnetic poles, which are not the same as Earth's geographic pole. The magnetic pole near Earth's geographic North Pole is actually the South Magnetic Pole. When it comes to magnet, opposites attract. The north end of a magnet in a compass is attracted to the South Magnetic Pole, which lies close to the geographic North Pole. A compass needle aligns itself and points toward the top of the Earth's magnetic field, always pointing north. The Earth is like a giant magnet. The north end of the compass magnet is drawn to align with the Earth's magnetic field. To represent magnetic fields, magnetic field lines are used as a visual too. It describes the direction of the magnetic force on a north monopole at any given position. Earth's magnetic field is the magnetic field generated from the core of the Earth, that extends from the Earth's interior out into space called magnetosphere, where it interacts with the solar wind, a stream of charged particles emanating from the Sun. The magnetosphere shields our home planet from solar and cosmic particle radiation, as well as erosion of the atmosphere by the solar wind or CME, coronal mass ejections. While space might seem empty, it is full of cosmic radiation and other particles that are harmful to life. What does this have to do with the northern lights? When charged particles emitted by the Sun come into contact with the atmosphere, the resultant reaction excites the air particles, causing electrons to move into higher energy orbits further away from the nucleus. The resultant effect is visible as an aurora. Now, we're all done with the distinct features of our early Earth during its formation. This time, we will discuss the possible outcomes of the collisions that took place in the formation of Earth. First, formation of the Moon. This is supported by giant impact hypothesis. The Earth spewed some of its mantle materials into outer space to become the Earth's only satellite, the Moon. This can be proved by the Apollo missions. Lunar rocks, or rocks from the Moon brought back to the Earth by the Apollo missions, have the same composition as the rocks on Earth that are derived from mantle materials, such as those erupted by volcanoes in the ocean floor. Question. It is the key component for all known life forms on Earth. It can form many different kinds of bonds and form essential compounds. All living things contain this element in some form. Answer. Carbon. Carbon is the primary component of macromolecules, including proteins, lipids, nucleic acids, and carbohydrates. Carbon's molecular structure allows it to bond in many different ways and with many different elements. The early Earth did not contain carbon. Carbon is built up by nuclear fission in which formed from the debris of a previous supernova. That collisions contaminated our planet with carbon. It is also present in the atmospheres of many planets in the form of carbon dioxide. Question. What do you call the process of releasing gases in the atmosphere during volcanic eruptions? Answer. Volcanic outgassing. Volcanic eruptions spewed gases from Earth's interior to the atmosphere, a process called outgassing that continues today. Most of the gas was carbon dioxide and water vapor. The water vapor condensed to form part of Earth's oceans as the surface cooled. That leads to breaking of Earth's crust. Collisions caused the crust initiating volcanic on the fractures. The fractures became the centers of volcanic areas, realizing molten rock materials and large volume of gases, or the process of volcanic outgassing. The violent collision that formed our Moon may have tilted Earth, too. The fact that the Earth is tilted on its axis is what's responsible for giving us different seasons. And it's why the southern hemisphere is getting ready for winter, at the same time the northern hemisphere is heading into summer. The poles remain cool because they are never tilted in a direct path of sunlight. During the winter, when a pole is tilted away from the sun, there is no daylight at all. However, during the summer, a pole receives sunlight all the time and there is no night. Polar day occurs when the sun stays above the horizon for more than 24 hours. Polar night occurs when the night lasts for more than 24 hours. There is no direct evidence for water for the period between 4.6 billion and 3.9 to 4.0 billion years ago. Thus, ideas concerning the early history of the hydrosphere are closely linked to theories about the origin of Earth. That much of the water on the planet was delivered by comet and meteor impacts. Question. It is the earliest life forms to evolve. The composition of the early atmosphere was gradually changed by using carbon dioxide in the atmosphere to manufacture their food. Answer. Cyanobacteria. Cyanobacteria are said to be the architects of Earth's atmosphere. Also called blue-green algae, are an ancient group of photosynthetic microbes that occur in most inland waters and that can have major effects on the water quality and functioning of aquatic ecosystems. Its early atmosphere was probably formed from the gases given out by volcanoes. It is believed that there was intense volcanic activity for the first billion years of the Earth's existence to gradually form the atmosphere of toxic gases but without oxygen. Evolution of cyanobacteria in the stromatolites, or the rock layers built by the blue-green algae, led the production of oxygen on Earth's atmosphere. What makes a planet habitable? A planet's habitability, or ability to harbor life, results from a complex network of interactions between the planet itself, the system it's a part of, and the star it orbits. The standard definition for a habitable planet is one that can sustain life for a significant period of time. There are many planets in the entire universe, but as far as we know, there is only a handful which could possibly support life. Space scientists and astronomers continuously scour the vastness of space for finding signs of life elsewhere in the solar system and even outside of it. So, what are the requirements for a planet to support life? Factors that make a planet habitable. It has to be a comfortable distance away from a star or has a habitable zone. The stars around it have to be stable. It should not have a very low mass. It must rotate on its axis and revolve. It should have a molten core. It should hold an atmosphere. In recent years, there has been a great deal of talk about finding liquid water on Mars and the possibility of life existing on the red planet. To better answer that question, let's look at the various factors that make a planet habitable. Take a look at the table. Read each of the factors and the corresponding implications depending on its characteristics. What will happen if these factors became too much, in right amount, or not sufficient to provide? In this way, you can compare the different factors to make a planet suitable to support life. If you're done, you can proceed to the first activity on Lesson 2. Lesson 2: Formation of the unique Earth activity. Activate. What makes the Earth habitable? To provide the context of how unique or not our planet is, it helps to have a basic knowledge of the properties of our two nearest neighboring planets. What are the differences between these three planets?